Hi guys, welcome back. We're going to continue on with 1.1 day 2, and we're going to talk about prime factorization today. So if we go ahead to our notes. So prime factorization is writing a number as a product of primes. Okay, so we write down all the prime numbers that multiply together to be that number. And this can be very helpful in a number of situations. And just a reminder, a prime number is a number that is only divisible by itself and 1. So some examples would be 2, 3, 5, 7, 11. Just because it's an odd number does not mean it is prime, okay? Also, some things to remember is some divisibility rules, okay? Some of these we know, some of these we don't. So if a number is divisible by 2, the last digit is even, so 0, 2, 4, 6, 8. So most of us know if we have an even number, it's divisible by 2. By 5, it either ends in a 0 or a 5, okay? Another one to maybe add would be 10. So that means that the last digit is 0. Okay. Now, one we don't talk about very often is 3s, okay? 3s can be kind of difficult after we get past maybe 30 or 40, okay? So if we have a digit, so let's say we have the number 369. If I add up all those digits, so 3 plus 6 is 9, plus 9 is 18, I know that 3 goes into 18, so 3 must go into 369. If we had the number 4,567, so 4 plus 5 is 9, and 6 plus 7 is 13, and 9 plus 13 is going to be 22. So 22 is not divisible by 3. If I wasn't sure, I could add these digits again together. So 2 plus 2 is 4, and 3 definitely doesn't evenly go into 4. So I know it doesn't go into 22 or 4,567. So if you want to know if a number is divisible by 3, all you have to do is add up the digits. Okay, and if the digits that add up is divisible by 3, it works out. So we're going to go ahead and decide if, define the prime factorization of each of these numbers. Sorry, I lost my train of thought there. Okay, and we're going to do that by finding our factor trees, okay? Some of you might have used factor ladders back in 6th grade, and that's fine if you want to use that. So I like my factor trees because if I don't know a prime number off the top of my head, that's okay. So I'm going to think, what two numbers multiply to be 81? And I know off the top of my head that 9 times 9 does. And neither of those are prime numbers. So 9 breaks down into 3 times 3. Now I know 3 is prime and 3 is prime, so I'm going to go ahead and circle those. And this 9 would have the same thing, okay? Once I've broken it down, these numbers no longer mean anything to me, okay? So I know that I can break 81 down into 3 times 3 times 3 times 3. And I can write that in exponential notation as 3 to the 4th. So I've now written the prime factorization and the exponential notation. Let's go ahead and try 1,125. Now, again, using our rules, I know that since it ends in a 5, it's divisible by 5. And I also know that 5 is a prime number, so I'll circle it. So 1,125 divided by 5 would be 225. Again, I can use the same principle that I know that 5 goes into 225 and divide that by 5. And if I divide that by 5, I get 45. And again, I know to circle my 5 because it's prime. So I know that 225 is useless to me now. 45 is going to go ahead and break down into 5 times 9, which I can circle, and I know 9 is 3 times 3. Okay. I'm going to go ahead and just shrink this just a little bit so it fits better on my page. So now, we usually do this in descending order, okay? And again, the 45 and 9 don't mean anything to me because I've already broken those numbers down. So I have 2 3s and 3 5s, so I'm going to have 3 times 3 times 5 times 5 times 5. So that is the prime factorization. And if I write this in exponential notation like we did yesterday, this would be 3 squared times 5 to the 3rd. I can't combine the 3 squared and the 5 cubed because they have different bases. Okay, let's try another one here. So 625. Again, I can tell that that's going to be divisible by 5. And 625 divided by 5 is going to be 125. 125 is divisible by 5, and 25, and 5 is prime, and 25 becomes 5 times 5, which again I'm going to circle. And I can ignore 125 and 25, and there are 4 5s. So 5 times 5 times 5 times 5 is equal to 5 to the 4th. If you want to go ahead and jump right to that, that is fine, because if you're like, oh, I wrote down 4 5s and I know that's 5 to the 4th, that's fine. Go ahead and try that. All right. Go ahead. We're going to look at 1470. Now, again, this ends in 0, so I'm going to say 10 goes into it 147 times. And 10, I know, breaks down into 5 and 2, which are both prime numbers, so I can ignore the 10 now. 147 is a little trickier, so I'm going to use my 3's trick because I know 2 doesn't go into it. So 1 plus 4 is 5, plus 7 is 12. So since 3 goes into 12, I know 3 goes into 147. It's also prime. 147 divided by 3 is 49. And 49 is 7 times 7, and both of those numbers are prime. And again, I can ignore the 147 and 49 because I've already broken them down into their prime numbers. So I'm going to write this, and I always write them in numerical order. So I have a 2, I have a 3, I have a 5, and I have 2 7s. So if I write this in exponential form, this would just be 2 times 3 times 5 times 7 squared. We could have invisible ones here in front of the 2, 3, and 5 if we'd like, but you don't have to. Up to you. I don't care either way. Typically, we don't write the ones there. All right, go ahead and try on your own 630. So if I were going to do this factor tree, I'd have 10 times 63. I know that 10 is 2 times 5, and both of those are prime. Sorry, that's kind of a bad 5. I know 63 is 7 times 9, and 7 is prime. And 9 is 3 times 3. So the prime factorization of that, if I shrink this guy down a little bit, would be, if I circle my 3's, 2 comes first here. 2 times 3 times 3 times 5 times 7. So this would be 2 times 3 squared times 5 times 7. Okay, we're not going to work through example 6 in the book right now. All right, I think that's all we have for today. Have a wonderful day, and I will see you tomorrow. Bye.